Hello students, in this video let us discuss what is Z transform and where it applies more and some properties and standard Z transforms. In signal processing, Z transform is used to convert discrete time domain signal into discrete frequency domain signal, whereas Fourier series and Laplace transform are used to study signals in a continuous time to convert continuous time domain to continuous frequency domain. So what is the difference between continuous time signal and discrete time signal? If we take the graphical representation of continuous and discrete, so in a continuous time graph you can draw like this. In a discrete you can take R, you can take, this is N we represent, this is T, where T is the time, N is also a time in a discrete time domain, we say it is a N. So this is continuous graph, this is a discrete time graph. In continuous time signal, we can define all interval of time. For example, if they are asking signal at the point, for example here 0.001, you can trace that point, trace the value of the frequency. But in discrete time signal, we cannot trace the value as continuous time interval. Here you cannot trace for decimal values because it is given for discrete, nothing but here -1, -2, -3, it's a +1, +2, +3, exactly given for the integer values. That is the difference between continuous and discrete time signals. And also in continuous time, in Fourier series Laplace and in Laplace transform, independent variable is time. Means in a continuous independent variable is time, and it is indicated by T also, letter T. But in discrete time signal, time is taken in terms of T only, but it is indicated by N. So because it is a integer, so it is more used in signal processing to convert the discrete time signal to frequency domain representation. Let's see now what is the Z transform mathematically defined. If Un is f of n, you can see here, so we are considering n term because our n values are integers for all n equal to 0, 1, 2, 3, so on. And Un is 0 for all n negative. So -1, -2, -3 for all negative value, Un, the function, nth function will be 0. Then Z transform of that Un is defined by Zt of Un symbolically, or you can also denote this as U bar Z, because we have the definition is summation n equal to 0 to infinity Un Z power minus n whenever the infinite series converges. This is provided when the series is convergent. So U bar Z, because when you expand this series by giving the n value and the simplification gives us the Z term. Means mathematically when you operate Z transform on nth term, your answer will be Z term. So time to frequency, time domain to frequency domain, when the time is discrete, we can apply the Z transform. Here we have the properties, basic properties, and need to understand to solve the problems, and very important to understand these. Firstly, we have linearity property, means Z transform of alpha Un plus or minus beta Vn, where alpha and beta are constants. So you can separate in this way. Alpha keeping constant, keeping as it is, Z transform operating on first nth term Un, plus or minus based upon which sign given, plus or minus beta, second constant keeping out, z transform of Vn. So what you have to understand from this, when the function is in a linear, means plus or minus format, you could separate. If it is in product and division format, it is not separated accordingly. Means for example, z transform of two functions un into Vn cannot be written as z transform of un into z transform of Vn. This is not true. So only linearity property is present. Next we have the one important property, it is called damping rule. We have two damping rules, that is if z transform of un is u bar z, it's a definition, because operating z transform on nth term we get the z term. Okay, then what damping rule states, z transform of k power n into un, for example k is some value like 2 power n into some nth term, it is u bar of z by k. This is the first damping rule. Second one, z transform of k power minus n un is equal to u bar of kz. Means in the z place we get z by k. When you have k power n into un, in the place of z we get kz when you have k power minus n into un. Here I given the proof for the first one, for first damping rule. By the definition, so what is the definition of z transform? Z transform definition is, z transform of un is summation n equal to 0 to infinity, this on which you are taking un z power minus n. So using that definition, we have here what on which you are operating z transform, k power n into un. So that is in the place of un we should take un is what? K power n into un. So k power n into un under the summation, and this z power minus n we are writing as it is. Now according to the definition, z having the negative power. So observing that, keeping that in mind, we keep un as it is, and I'll shift this k power n to the denominator, then it will become k power minus n. If you shift this, so this k power n can be written as 1 by k power minus n. So then z by k power minus n. Now comparing this with the standard definition, we have un is un itself, only the change is z place is z by k. So this can be written as u bar z, this is u bar z. So in the place of z we have z by k, so we can write this as u bar of z by k. So means when you have the result k power n into n, you have to replace z to z by k. So this is a first damping rule. Similarly, you can prove the second damping rule by applying the z transform. The next important property is, it is z transform of n power k is equal to minus z d by dz of z transform of n power k minus 1. Okay, this is very important property. We have some standard result to prove that this is very much required. Okay, now by the definition of z transform, what is the z transform definition? Z transform of un is equal to summation n equal to 0 to infinity un z power minus n. By this definition, un is n power k minus 1. So that's equal to, where you have un, that writing as n power k minus 1 z power minus n. Now we are considering the right side of the proof required. So this is easy to prove the result. So let us consider z transform of n power k minus 1. Now next, step by step, let us think. Next we go for differentiating of this. So we have z transform of n power k minus 1. Let us differentiate with respect to z. So d by dz, both the side. Z transform of n power k minus 1 and d by dz. And here when you are differentiating, this n term is a constant. We differentiate this z power minus n. When you differentiate z power minus n, it is what? Minus n z power minus n minus 1. Okay. Now we have this d by dz of z transform of n power k minus 1. Now I'm writing this is reverse here in this step. So summation n equal to 0, we have this n power k minus 1 and this n, and z power minus n minus 1, and I am shift this minus to other side. It is minus d by dz of z transform of n power k minus 1, because we have minus here. Now just we multiply what is required for the complete RHS z. We have because minus d by dz. So you multiply z both the side we get. So if you multiply, what happens here? This is z left side and summation n equal to 0 to infinity, and taking the power added, it become n power k. Okay, then this can be written as z power minus n by z, and other side this comes as it is. Okay, now so this z gets cancelled. We get, this is according to the definition of z transform, un is n power k. So therefore z transform of n power k can be written as z transform of n power, z transform of un can be written as z transform of n power k will be the result minus z. When you multiply other side z, it gives us minus z d by dz of z transform of n power k minus 1. Okay, that's our required proof. This is very important proof to prove the result of z transform of n, taking a k is 1, z transform of n square, z transform of n cube. These are very much required for our discussions. Next we have shifting property. There are two types of shifting property. One is right shifting property, that states that if z transform of un equal to u bar z, the right shifting property states that z transform of un minus k, where k is some value like 1, 2, 3, 4, 5, 6, is equal to z power minus k. When you have n minus k, it will be z power minus k u bar z, where k greater than 0. This is a right shifting property. So we have the other property, left shifting property, or we can say left shifting rule. This is very important for our discussion, left shifting rule. So that states that z transform of un plus k. So what, see the difference here, minus k for right shifting rule plus k for the left shifting rule, is equal to z power k u bar z minus summation r equal to 0 to k minus 1 u r z power minus r. See, when you expand this in general, what we get, this gives us z transform of un plus k gives us z power k, and in the bracket u bar z minus, it start like that. When you expand this series, we get u naught minus u1 z power minus 1 minus u2 z power minus 2, and so on, continuing, ending at u k minus 1 z power minus k minus 1. So when you expand, this is in general we have. Now we want particularly when k equal to 1, k equal to 2, k equal to 3. This is required when you are solving the problem. Suppose k is 1. See here, n plus 1, un plus 1. It will be z power 1 because k is 1. And u bar z, and where it will end when k is 1. So u 0, z power minus 0. Z power 0 is 1. So u naught. So you understand in this way, after n, if you have 1, if the k value is 1, after u bar z, let us enter in general series, is a 1 term. If you have k is 2, after u bar z, we have to take the 2 terms. After u bar z, for the third k is 3, we have to take 3 terms. Likewise, you can continue based upon the k value. This is our shifting property, and we have 2 shifting property. In that, we are using very much left shifting rule. Next, we are discussing z transform of some standard functions. Okay. We have some set of functions. For that, we can remember the formulae and obtain the result directly. So firstly, we have z transform of k power n, where k is some result number. So this is z by z minus k. So this is proved as z. We know that z transform of un by definition is summation n equal to 0 to infinity un z power minus n. When un is k power n, z transform of k power n is what? N equal to 0 to infinity summation un is k power n z power minus n. and we expand this summation by giving n values 0. By giving n value is 0, so this is n is 0, k power 0 1, z power 0 is 1. So 1 into 1 1. Next, by giving n is 1, it will be k. You can write this as easily to write the result summation n equal to 0 to infinity k by z power n. Now n equal to 0, it is 1. N equal to 1, it is k by z. N equal to 2, k by z whole square, and so on. So this is in the standard form of 1 plus x square and so on. So by binomial theorem, this can be written as 1 minus x power minus 1. Therefore, here in the place of x we have k by z. Therefore, you can write this as 1 minus k by z power minus 1. So that can be written as 1 divided by 1 minus k by z. Then z is a LCM. In the denominator taking, we get z minus k, and divide by z goes to the numerator. So we get the result z transform of k power n is z divided by z minus k. For example, z transform of 2 power n, it is z by z minus 2. And from this you have to remember one more standard result. From this you can write z transform of 1 is what? You can write z transform of 1 as 1 power n. So it is z by z minus 1. The second important result, standard function, z transform of n is z divided by z minus 1 whole square. So here you can use the property we have already proved. Z transform of n power k is given as minus z d by dz z transform of n power k minus 1. We have this property, and by substituting k is what value we get, n is 1, n we is substituting k is 1. So substituting k is 1, we get z transform n power 1. So z transform of n, that is required. According to this property, minus z d by dz z transform of n power, where k is 1, 1 minus 1 0, n power 0. So what is n power 0? It is z transform of 1. This will become z transform of 1. Okay, z transform of 1 is z by z minus 1. So you written minus z d by dz z by z minus 1. So while differentiating this, applying quotient rule. So if you apply quotient rule, we get z minus 1, differentiation of the numerator z is 1, minus z, differentiation of the denominator z minus 1 is 1, divided by z minus 1 whole square, minus z plus z gets cancelled, we get minus 1 divided by z minus 1 whole square. So we have outside minus z, and this minus 1 divided by z minus 1 whole square, both minus into minus gets cancelled, we get z by z minus 1 whole square. So this is z transform of n. Similarly, if you take k is equal to 2, k equal to 3, and differentiating by applying quotient rule, we can obtain the result z transform of n square is z square plus z divided by z minus 1 whole cube, and z transform of n cube is z cube plus 4z square plus z divided by z minus 1 whole power 4. The next important result, using damping rule, second property. So we can prove this result. We have here z transform of k power n into n is equal to kz divided by z minus k whole square. We have already the result we have proved in a previously. Z transform of n is what? Z by z minus 1 whole square, that is u bar z. Okay. Now by damping rule, we can write what is in general damping rule, z transform of k power n into un is u bar of z divided by k. Okay, here un is in our problem n. So therefore, in z transform of un nothing but u bar z. In u bar z, we have to change z to z by k. So that is z by k divided by z minus k minus z by k minus 1 whole square. Then if you simplify this, taking LCM, it is z minus k whole square divided by k square in the denominator. Then k gets cancelled, 1 k is remaining, that goes to the numerator. We get the result kz divided by z minus k whole square. This is by damping rule, and it is very, very important when you are solving inverse Z transform problems. Similarly, after finding Z transform of n square and n cube, changing Z to Z by K, we can obtain the result of Z transform of K power n into n square as K Z square plus K square Z divided by Z minus K whole cube, and Z transform of K power n into n cube as K Z cube plus 4K square Z square plus K cube Z divided by Z minus K whole cube. So we have another important result, that is Z transform of cos n theta and sin n theta. So we can prove both the result in a one procedure by considering Z transform of e power I n theta. Can be written as Z transform of e power I theta power n. Okay. So Z e power I n theta can be written as what? Cos n theta plus I sin n theta. And other side, Z transform of, this is in the form of Z transform of K power n. So this is what? Z by Z minus K, here where K is what? Where K is e power I theta. So therefore it is Z by Z minus e power I theta. And then this can be written as e power I theta. I will simplify. This is Z divided by Z minus of cos theta plus I sin theta. So you can rewrite this as Z divided by Z minus cos theta minus I sin theta. So next we have the conjugate. This is in the form of A minus IB. So what is the conjugate of A minus IB? It is A plus IB. So let us multiply A plus IB and divide by A plus IB according to the function we have. So therefore it is Z into conjugate of the denominator is Z minus cos theta A plus I sin theta, and denominator Z minus cos theta minus I sin theta, this is already we have. For this we are multiplying Z minus cos theta plus I sin theta. Okay, then the denominator in the form of A plus B into A minus B. This is A minus B into A plus B. This will be A square minus B square. So that is what? The denominator A square means Z minus cos theta whole square, and minus B square minus I square sin square theta. And you can write separating real and imaginary part in the numerator plus IZ sin theta when you multiply Z inside. Okay. Now we separate the real and imaginary parts in both the side. In the left side we have Z transform of cos n theta is real, Z transform of I sin n theta is imaginary. So let us separate. So Z transform of cos n theta plus I Z transform of sin n theta. This is in left. And the right side, Z into Z minus cos theta is a real, divided by complete denominator, it's Z square. When you expand, minus 2Z cos theta plus cos square theta plus sin square theta, because this minus I square is, this will become plus 1. Okay, I square is minus 1 plus 1. We get cos square theta plus sin square theta is plus 1. And we have plus I Z sin theta divided by same denominator Z square minus 2Z cos theta plus 1. So comparing both the side, real is cos n theta, result in the right, and imaginary is sin n theta, result in the right, imaginary. So Z transform of cos n theta is Z into Z minus theta divided by Z square minus 2Z cos theta plus 1, and Z transform of sin n theta will be Z sin theta divided by Z square minus 2Z cos theta plus 1. You see here some standard function Z transform list, what we have proved so far, that's all listed. You go through this before solving the problems. In the next video, let us solve the problems on Z transform using this standard functions.